In this video, we will explain how to use the Laplace transform to solve this initial value problem. Maybe before I start solving the differential equation, I would like to remind you that the Laplace transform of A is A over S. The Laplace transform of e to the at is 1 over s minus a. The Laplace transform of the function t is 1 over s squared. And what I'm calling the most important property of the Laplace transform, which is that the Laplace transform of the derivative is s times the Laplace transform of y minus y evaluated at 0. Then we compute the Laplace transform of both sides of the equation. We use this property to say that this Laplace transform of the derivative is s times the Laplace transform of y minus y of 0. But y of 0 is negative 2, then is minus negative 2, which is plus 2. And then plus 3 times the Laplace transform of y equal to the Laplace transform of 2. Using this property, we get that this is 2 over s, and the Laplace transform of t is 1 over s squared. Then we get 3 over s squared. If I combine these two terms, I get that s plus 3 times the Laplace transform of y is equal to, I can move the 2 to the left, is negative 2 plus 2 over s plus 3 over s squared. And then this is just common denominator is s squared, is negative 2s squared plus 2s plus 3, and here is s plus 3 times the Laplace transform of y. How do we solve for the Laplace transform of y? I can just divide by s plus 3, and then I get that this is just s plus 3. Then the next step is to find the Laplace transform inverse of this. Notice that once I find the Laplace transform inverse of this, I'm finding a function f of t such that this is true. And then notice that from these two equations, I get that my y is just f of t. But how do I compute the Laplace transform inverse of this expression? We need to, as you will see in all these problems, you have to do partial fractions. Let's see, this is a linear term of order 2 with multiplicity 2. There will be a over s plus b over s squared. Let me erase this, that we don't need it anymore. And then it will be plus, this is a linear term, c over s plus 3. Then this is just the common denominator. We have to make sure to write down this denominator so that the two expressions have the same denominator. And then I get a times what is missing s to be this common denominator is missing an s and an s plus 3, plus b times what is missing s squared to be this denominator, and s plus 3, plus c times what is missing s plus 3 to be this denominator, just an s squared. Since these two fractions are the same and they have the same denominator, then we want this numerator, which is a s squared plus 3as plus bs plus 3b plus cs squared. We want that to be negative 2s squared plus 2s plus 3. Now let's set up the equations. Then what is the coefficient of s squared? Coefficient of s squared on the left, we have a plus c. We want a plus c to be, what is the coefficient of s squared on the right? Negative 2. What is the coefficient of s on the left? Is 3a plus b. And what is the coefficient of s on the right? Is 2. And what is the constant coefficient on the left? Constant coefficient is 3b. And the constant coefficient on the right is 3. Then let's solve the system. We can solve this first. We have that b is equal 1. Once we know that b is equal 1, then we get that a is 1/3. And once we know that a is 1/3, we get that c is -2 minus 1/3, and this is negative 7/3. Okay, then the whole point is that this can be written as a is 1/3, b is 1, and c is -7/3. So let me write it like this, -7/3. And we can forget about all of this. And all this work of Laplace transform was just to rewrite it like this. But now I can compute the Laplace transform inverse, because if we look at this formula and we compare it with this, we know that this is the Laplace transform of the function 1/3. And this part is the Laplace transform, so I erase this, of the function t. And this part is the Laplace transform. What is a when you compare these two? The 7/3 is going to be there, and here we will have an e to the, when you compare a is -3t. Then when you compare here and here, you get that the function y is 1/3 plus t minus 7/3 e to the -3t, that this is a solution of this differential equation. You can check that indeed this is a solution. For example, when you evaluate at 0, you get 1/3 minus 7/3, which is -2, and you can do the derivative of this and check that if you do the derivative plus 3 times this function, you get this function. Then, okay, this is it for this example.